In this video, we're going to run through the A-level physics required practical to calculate the Young modulus from an experimental setup. So this is usually in year 1 of physics A-level and is on pretty much all exam boards. So to start, let's just recap what the Young modulus is. So we usually use a capital E for it, and the Young modulus is defined as the stress per unit strain exerted on a material. Stress is the force per unit area, and strain is the extension per original length. If we combine those two equations together, we see the A drops down, and we also have the L at the bottom going to the numerator. So we're left with force times by the original length divided by the extension times by the area. Do note that delta L here could be X on other exam boards. It's delta L on your physics AQA equation sheet though. And note the units here as well. We've got extension and cross-sectional area both have to be in meters or meters squared for this to work. Okay, so the setup in the Young modulus practical is a little bit tricky, and it's one of those your teachers definitely have to set up for you. First of all, you need a reference wire, and then you need the wire you're actually going to do the testing on, called the test wire. So they both need to be hanging for quite a while with some weight on them originally to make sure they're not kinked or bent in any way and they're fully straight, and to mitigate the effect of any temperature differences or things like that. So here's what the method would be to measure the Young modulus in a practical way with a graph. The method is to first of all measure the diameter of the test wire with a micrometer in 3 different places. You could do it while it's set up, usually in a micrometer, 3 different places, then find a mean and calculate the cross-sectional area using pi d squared over 4. Then what you're going to do is measure the original length of the wire using a meter ruler or a tape measure, and again you can do this when this is already set up. Then once it's set up next to the reference wire, as I mentioned earlier, the idea is to ensure that any extension is not due to the wire straightening or any temperature differences or things like that. The reason you want it to be extending is because you're adding masses to the end. So the reference wire mitigates that. Then you're going to set the scale to 0, so it starts from 0, and then you're going to start adding masses to the test wire to increase the force. Bear in mind, force is going to be equal to the weight, which is mg. Then to measure the extension, you're going to use the vernier scale. Now the vernier scale is set up so that it's got 1 bit on the test wire, 1 bit on the reference wire, so you can see how much the test wire goes down compared to the reference wire. The reason we need this is because the extensions are quite small. They're unlikely to be more than a couple of millimeters, maybe a few millimeters at most. So the vernier scale allows us to measure to 0.1 of a millimeter in the resolution. Next, what we're going to do is just do that for 8 different masses and then try and find some do some repeats later, and then find a mean before we can plot our results on our graph. So on our graph, bear in mind that we said Young modulus is stress over strain. It might be tempting to just do a quick measurement of stress over strain, plot them on the graph, and then work out the gradient. However, that's quite a lot of effort, and it's not incorrect to do that, but the much better way is to just record the mass and the length, and then what you can do with your gradient, I'll show you later, you can convert it into Young modulus by using the constants in our calculation. So your graph should look like a straight line, and then it will start to curve off, because this is what ductile materials do. They're not proportional forever. Once they go past the limit of proportionality, then you're not going to be able to measure the Young modulus. Please see my other video about materials if you want a bit more detail on this. So you're going to measure the gradient for the straight part of the line. That's going to equal m over delta L, or the extension. Now, as we looked at earlier, when we talked about my equation for Young modulus, we said it was F times by L over extension times by area. Now I'm just going to change F here to mg because we're using m instead of g, because we can just times by g at the end. So in my expression, if I sort of show you what the m over delta L is the gradient, that means that if I find the gradient of the line, that's not the Young modulus, I still need to multiply by g, 9.81, and the original length, and then I need to divide the whole thing by the area. The idea is to save doing that to every value. If you just measure the mass and the extension, you can then just do this at the end, because they're just constants you need to multiply by. So in this case then, the Young modulus is just gradient times by Lg divided by the cross-sectional area in meters squared. And we're only using the straight part of the graph, but use the whole of the straight path. Don't just use a tiny bit. And that should give you a value for the Young modulus. Usually it's going to be in roughly gigapascals, but it depends on the material you're using. Next, let's talk about the uncertainties for this experiment. So the percentage uncertainty in the Young modulus is going to be a combination of the percentage uncertainty in the gradient plus the percentage uncertainty in the length plus the percentage uncertainty in the cross-sectional area. So how would you go about doing that? So the percentage uncertainty in the gradient would be if you're able to know what the percentage uncertainty in the mass and the extension are, then you can make error bars. And once you've done error bars, you'll have a line of best fit, and you can also draw lines of worst fit. That's the steepest or the shallowest line that goes through all the error bars. To find the percentage uncertainty in the gradient, you just do the difference between the gradient of the line of worst fit and the line of best fit, and then divide that by the line of best fit gradient times by 100 to make it a percentage. To work out the percentage uncertainty in L, you just do the resolution, so usually a millimeter, divided by the actual length in meters, therefore times by 100 gives you percentage uncertainty. To find the percentage uncertainty in the area, you need to do the resolution of a micrometer, which is 0.01 millimeters, divided by the actual diameter, and you times it by 2. Because the area is pi r squared, you double the percentage uncertainty in the diameter. The alternative, if you've done repeat readings, is to do the range of those values divided by 2 to find the uncertainty, and then to find the percentage uncertainty, then you've got to make sure you times by 2 for the same reason. Is because the cross-sectional area is pi d squared over 4, or pi r squared, so you're doubling that percentage uncertainty. So you'd add those all together, that'll give you a percentage uncertainty in the value for Young modulus. There's a couple of safety concerns to be aware of in this practical. The obvious one is if the wire snaps, if it goes into your eye, it'll be released with quite a lot of energy, that could be really dangerous. So we're going to wear goggles so that if the wire does snap, it doesn't go into your eyes. We're going to try and keep the masses close to the ground so that if they fall, they're not going to reach a high speed and people are less likely to stand underneath them. In terms of errors in this practical, the main one is just making sure the reference wire and the test wire are put under some stress originally with some masses on the end to make sure they're fully straight. Sometimes the wire can continue moving because it's just actually it's straightening out rather than actually due to being the extension on it. So that's the Young Modulus practical. If there's any questions you have, please comment below and let me know if you want to do a specific practical next. And thanks for watching.